Okay. Observation dates. Specify the observation date as a date object expression. AstroPosition Mars GCRS date now. GCRS date now. Dates are taken at any time system and converted into the TT time system. America, Los Angeles. I'm looking for New York. New York. AstroPosition. Date object. Random date. Time system. UT1. I'm just curious, what if I compare the different time zones with AstroPosition. Association map. So there's UTC, UT1, UTC smeared. So smeared UTC. And there's a difference. You have 39.6 and 36.6 here. TAI, TT. Date strings are assumed to be in the local time zone. The default smeared UTC time system and are converted into TT in time zone 0. So if I do Downloading ephemeris from Mars and its moons, 1980 to 2020. Some especially important dates can be given as named strings. Observation locations specify the geolocation where the XY plane of the horizontal frame is tangential to the Earth's surface. Location here. Observe the star frame epochs. Observe the star Vega on this date from your location using the mean frame of data. So I know this date equals now. Log equals here. Right ascension 1 hour 22 minutes. So I can do AstroPosition Vega meme date log. Perform the same observation on the same date from the same location, but now using the mean frame of 100 years ago, which is different from the current frame due to precession. Date log epoch date minus 1 century. So now I have 18 hours 37 minutes 41.4 seconds versus 8 hours 34 minutes 19.9 seconds and 38 degrees 43 minutes 16.5 seconds compared to 38 degrees 43 minutes 2.9 seconds. Astrometric corrections. Position of Mars at the current instant in the main PCRS coordinate system of the solar system. Okay, so we'll set day equals now. Geo equals AstroPosition. Geo equals AstroPosition. Mars. TE. Date. Light time. Geometric. AstroPosition. Okay, so you have 4 hours, 24 minutes, 0.6 seconds, 24 degrees, 28 minutes, 0.5 seconds. Position of Mars when the light was emitted that arrived at Earth's center at that instant. Wait, let me think of this. So, obs equals AstroPosition Mars TE date light time observation So you have 4 hours, 23 minutes, 59.5 seconds compared to 4 hours, 24 minutes, 0.6 seconds. The difference is on the order of tens of arc seconds. Unit convert. Well, here, let me just calculate this real quick. AstroPosition angular separation, geo obs, milliradians. Oh, it's on. Let's go to microradians. Nano 71349.7428763 nanoradians. Position of Mars from receiving light emitted from Earth's center at that instant. EMS equals AstroPosition Mars TETE date light time emission. The difference is similar. That's interesting. Let me do it nano. So you have 71348 compared to 71349. Eddington observed this star during a solar eclipse on May 29, 1990. Star equals HIP 20842. Locus equals Principe Island. Date equals date object 1919 5 29 14 15 35. Time zone equals 0. So that's Thursday 29 May 1919 14 15 35 GMT. The sun and moon were essentially the same position. So we have AstroPosition, sun, equatorial, date, log, AstroPosition, moon. What's going on here? I'm trying to. Moon, equatorial, date, log. This was the observed position, including light deflection. Sun deflected equals AstroPosition. HIP 20842. No. What's the name of this star? G star. HIP 20842. Entity star. HIP 20842. Entity star HIP 20842. Non-missing property association. Alternate names HIP. Says alternate name HIP 20842. Classes. Sun deflected equals AstroPosition. Equatorial date loc. This was the observed position including light deflection. I already did that one. This would have been its position with no light deflection. No deflection. Basically I'll copy what I typed above. Down. No deflection equals light deflection. It's false. Oh, why didn't that work? Oh. The difference is about 1 arc second. Unit convert. Sun deflected, no deflection. Astro angular separation. Nanoradians. 4,941.225.29575 nanoradians. The Shapiro effect introduces a small delay in light propagation for light rays that pass near massive bodies like the Sun, which also affects positions. Observe Venus on this date. Quantity, AstroPosition. Quantity, AstroPosition, Venus. Equatorial date object 2022 10/23/000. Right ascension, angular degrees, so 208.141293061 degrees. Then if we run this again and we do gravitational time delay, false, we get 208.141293066 6. Differences are very small in the order of micro arc seconds. So now if we do unit convert minus nanoradians, we get, okay, we're gonna have to go to picoradians because it's picoradians. This one, so we have a positive quantity, minus 11.42904744943 picoradians. So picoradians. Observed positions change due to the motion of the observer. For example, the orbital motion of the Earth around the Sun. Date equals now. This is the current observed position of Polaris. AstroPosition, Polaris, GCRS, date. This would be its position with no correction for aberration. So I can do aberration, false. So notice it's 49.1 seconds compared to, well, it's 32 minutes and 14.5 seconds compared to 31 minutes, 49.1 seconds. 6 months later, the aberration correction will have the opposite sign. So if I do, we're going to do date plus quantity 6 months, we get 2 hours 31 minutes 49.2 seconds. The instantaneous rotation of the Earth, the instantaneous rotation, alright, whoops, I was supposed to do aberration true. So okay, so where was I? So if we have no correction for aberration, we get 2 hours 31 minutes 49.1 seconds. Now if we add 6 months, we make aberration true, and we'll have 2 hours 31 minutes 21.6 seconds. I don't know what they mean. We'll have the opposite sign. Let me look that up real quick. Equatorial. Wikipedia aberration astronomy. There we go. Phenomenon where In astronomy, aberration, also referred to as astronomical aberration, stellar aberration, or velocity aberration, is a phenomenon which produces an apparent motion of celestial objects about their true positions dependent on the velocity of the observer. It causes objects appear to be displaced towards the velocity of the motion of the appear to be displaced towards the direction of the observer. It causes objects to be displaced towards the direction of the motion of the observer compared to when the observer is stationary. The change in angle is on the order v divided by c, where c is the speed of light and v is the velocity of the observer. In the case of stellar or annual aberration, the apparent position of a star to an observer on Earth varies periodically over the course of a year as the Earth's velocity changes as it revolves around the Sun by a maximum angle of approximately 20 arc seconds in right ascension or declination. The apparent position of a star viewed from the Earth depends on the Earth's velocity. The effect is typically much smaller than illustrated. So you have Earth, you have v, moving at speed, velocity, and you have this angle, rest frame, moving frame. The term aberration has historically been used to refer to a number of related phenomena concerning the propagation of light in moving bodies. Aberration is distinct from parallax, which is a change in the apparent position of a relatively nearby object as measured by a moving observer relative to more distant objects that define a reference frame. The amount of parallax depends on the distance of the object from the observer, whereas aberration does not. Aberration is also related to light time correction, relativistic beaming, although it is often considered separately from these effects. Aberration is historically significant because of its role in the development of the theories of light, electromagnetism, and ultimately the theory of special relativity. It was first observed in the late 1600s and by astronomers searching for stellar parallax in order to confirm the heliocentric model of the solar system. However, it was not understood at the time to be a different phenomena. In 1727, James Bradley provided a classical explanation for it in terms of the finite speed of light relative to the motion of the Earth in its orbit around the Sun, which he used to make one of the earliest measurements of the speed of light. However, Bradley's theory was incompatible with 19th century theories of light, and aberration became a major motivation for the ether drag theories of Austin Fresnel in 1818 and G.G. Stokes in 1854, and for Hendrik Lorentz's ether theory of electromagnetism in 1892. The aberration of light, together with Lorentz's elaboration of Maxwell's electrodynamics, the moving magnet and conductor problem, the negative ether drift experiments, as well as the physio experiment, led Albert Einstein to develop the theory of special relativity in 1905, which presents a general form of the equation for aberration in terms of such a theory. So if we go down, aberration may be explained as the difference in angle of a beam of light in different inertial frames of reference. A common analogy is to consider the apparent direction of falling rain. If rain is falling vertically in the frame of reference of a person standing still, then to a person moving forwards, the rain will appear to arrive at an angle requiring the moving observer to tilt their umbrella forwards. The faster the observer moves, the more tilt is needed. The net effect is that light rays striking the moving observer from the sides in a stationary frame will come angled from ahead in the moving observer's frame. This effect is sometimes called the searchlight or headlight effect. In the case of annual aberration of starlight, the direction of incoming starlight as seen in the Earth's moving frame is tilted relative to the angle observed in the Sun's frame. Since the motion of the direction of the Earth changes during its orbit, the direction of this tilting changes during the course of the year and causes the apparent position of the star to differ from its true position as measured in the inertial frame of the Sun. While classical reasoning gives reason for aberration, it leads to a number of physical paradoxes observable even at the classical level. See history. The theory of special relativity is required to correctly account for aberration. The relativistic explanation is very similar to the classical one, however, and in both theories, aberration may be understood as a case of addition of velocities. Classical explanation, relativistic explanation, relationship to light time correction, and relativistic beaming. Types: stellar aberration, planetary aberration, hypotheses. Okay, well that's interesting, but let me go back to here. Okay, 6 months later, the instantaneous rotation axis of the Earth rotates around the geographical polar axis of the Earth, introducing small corrections in the positions of objects with respect to the ITRS and horizon frames. So we can set the date equals now. Day equals now. The angular differences can be obtained from geo-orientation data. Geo-orientation data. Date, polar, motion. Let me just do geo-orient. So we have geo-orientation is an experimental function. When was this introduced? I didn't know this thing. 12.3. Basically, it gives geoorientation data gives information about the orientation of the Earth with respect to the celestial reference frame. Whoa, this is very advanced. Applications. Well, I can read about that later. But so we have geoorientation data, date, polar. Actually, here, let me delete one of these. I think so. We can do geoorientation data, date, polar motion. So now we have 0.043 arc seconds and arc seconds. By default, the ITRS. Let me X this out. By default, the ITRS and horizon frames use measured values of polar motion. So we can do AstroPosition. Let me copy this. So AstroPosition. And then we do horizon date here. Here is the location. So we get azimuth 147 degrees, 52 minutes, 35.1 seconds. Altitude 28 degrees, 25 minutes, 58.2 seconds. And if I go down, it says this would be the position of Sirius without taking into account polar motion. So I have AstroPosition, Sirius, star, horizon, date, here, polar motion, none. None. I need to capitalize that. None. And here is not a valid location specification. Here. So azimuth 147 degrees, 52 minutes, 35 seconds. Altitude 28 degrees, 25 minutes, 58.5 seconds. Let me go down. Specify your own values of polar motion. So I can do AstroPosition, horizon, date, here, polar motion. I can just make something up, quantity. Let me see here. Do I have to specify a list? So I could do E and 2E, or how do I do Euler gamma, arc seconds. So let me close that bracket. So I can have AstroPosition, azimuth, and altitude. So notice it's 35 here, 36.6 here, 56.8 here, 58.5 here. Compute the time of sunset on this date. Okay, so we have sunset equals sunset date object 2022 9/26. Let me evaluate that. So that's Monday, 26 September 2026 here. Let me do date. Let me do a different date object. Let me do 2021. Let me do 11/28. Okay. So Sunday, 28 November 2021. This is the time. Well, actually, I'll just use there. There's okay, so date object 2022 9/26. Okay, so it's Monday 26 September 2022 18:20 GMT -5. Why is that more precise is my question. Okay, anyways, that is the time when the upper limb of the sun touches the horizon on its way down. So the sun's center already has negative altitude at that time. So if we do AstroPosition, sun, and then we evaluate that, we have horizon, sunset here. So azimuth 268 degrees. The altitude is negative. It's negative 0 degrees, 10 minutes, 33.1 seconds. By default, horizon computations on Earth use a refraction model. Without it, this would have been the position of the sun at that instant. So we can see, we can copy this and change. So we can see here we have refraction, none. So now the azimuth is 268 degrees, 39 minutes, 39.3 minutes. The altitude is negative 0 degrees, 46 minutes, 33 seconds. The difference is approximately 36 arc minutes for standard atmospheric conditions. Specify our own conditions of pressure, temperature, and relative humidity, as well as the light wavelength. That's awesome. So I can do like, so I can copy what I have above. I could do refraction equals, start a list. I could do quantity 1000. I'll do 1031 millibars. Now do quantity 0. Shit, I think this 0 0C. Good to get that right. Okay, 0 degrees Celsius. 40 quantity 40%. Quantity. Oh, that's relative humidity. This percent is for, so 40% relative humidity, 0 degrees temperature, and then quantity would do 550. Let me do 550 nanometers. Okay, so now we have AstroPosition, azimuth. We have altitude -0 degrees, 8 minutes, 25.9 seconds. If I go down, it lists the refraction details. And so that's cool. So it lists like the extra specifications. So coordinate systems. Coordinates are given by default in spherical form as longitude latitude pairs. AstroPosition quantity 6.5 hours of right ascension, quantity -10.12 angular degrees, quantity 3.4 astronomical unit equatorial. So let me do this. AstroPosition quantity 6.5 hours of right ascension. Let me evaluate that. Just that symbol, it's like a backtick. Then there's quantity -10.12 angular degrees, and then quantity 3.4 AU. Oh, I think that backtick is like meaning it's a numerical quantity, and then equatorial. So right ascension 6 hours 30 minutes 0.0 seconds. Okay, convert to Cartesian coordinates, still in the same equatorial frame. So then I can do AstroPosition %5 equatorial Cartesian, and I get x coordinate -0.4366885 AU, y coordinate 3.31847 AU, z coordinate -0.5974115 AU. Convert to cylindrical coordinates, so then I can do the same thing right here, but this time instead of doing Cartesian, I'll do to cylindrical, and I'll get right ascension 6 hours 30 minutes 0.0 seconds, xy distance 3.3471 AU. You get z coordinate -0.5974115 AU. Expressed in a given cartographic. Now let me just Google cylindrical coordinates just to look at a picture real quick. Cylindrical coordinate system right there. So basically how it works is there's an angle here, there's the radius, the radial distance, the angular coordinate, and the height. So there's the angle, the xy distance, and the z coordinate. Expressed in a given cartographic projection. So I can do Molly weed, for example. I can do Mol weed. So I can do AstroPosition 1.51731 085 118 -0.1979. 1957924333972 TETE date Tuesday 17 January 2023 02:43:18.269 TT mall weed. Compute spherical horizontal coordinates for the moon. So I can do moon equals AstroPosition moon, and I get the altitude and azimuth. Compute SEU Cartesian coordinates. So AstroPosition moon horizon Cartesian SEU. I get S coordinate negative 101467 kilometers, E coordinate 156597 kilometers, U coordinate negative 331836 kilometers. Use Cartesian coordinates with a different orientation. So now I can do AstroPosition moon horizon Cartesian ENU. So instead of southeast up or something, it's like east north up. So now I get east is 156597 kilometers. I think the numbers are the same, but they're in different order. Use cylindrical coordinates using hour angle. So I can do AstroPosition moon ITRS cylindrical HA, and I get hour angle is negative 10 hours 16 minutes 31.2 seconds. XY distance 359030 kilometers. Z coordinate negative 126614 kilometers. Properties. Extract properties from an AstroPosition object. So I can do AP equals AstroPosition Sirius, which is also called the dog star, Sirius, and I can extract coordinate properties. So I can do AP data. Angles are given as numbers of angular degrees, so I can do AP azimuth. I can get the altitude, AP altitude. Distance from the frame origin is given in astronomical units, so I can do AP distance 543,645.343585. I can extract the frame properties, so I can do AP, no, I need a semicolon, AP frame. Get horizon date Tuesday 17 January 2023 024722.679 TT. Location geoposition 38.4118584 negative 82.4324103. I can get the frame name AP frame name, which is horizon. I can get the date of observation. I can just do AP date Tuesday 17. Same thing as here. Location of observation and frame origin. AP location. I can extract the coordinate system or projection being used, so I can do AP coordinate system north as alt. And that is the end of the section on properties. This is the larger section, the end of this section, scope for the AstroPosition function introduced in Mathematica. So I'm going to end this recording.